Voltage drop is a crucial concept in electrical engineering and circuit design. It refers to the decrease in voltage as electricity flows through a conductor. Understanding and calculating voltage drop is essential for ensuring that electrical devices receive the appropriate voltage levels for proper operation. The formula for voltage drop is voltage drop equals current times resistance. In this formula, voltage drop is typically measured in volts, current is measured in amps, and resistance is measured in ohms. Current represents the flow of electrical charge through a circuit. It is the amount of charge passing a given point per unit of time. Resistance is the opposition to the flow of current in a circuit. It is a property of the material through which the current is flowing. The higher the resistance, the more voltage is needed to push a given current through it. To calculate voltage drop, you simply multiply the current flowing through a conductor by the resistance of that conductor. For example, if a circuit has a current of 10 amps and a resistance of 2 ohms, the voltage drop would be 10 amps times 2 ohms, which equals 20 volts. This means that the voltage at the end of the conductor will be 20 volts less than the voltage at the beginning of the conductor. There are several factors that can affect voltage drop in a circuit. Firstly, the length of the conductor plays a significant role. The longer the conductor, the higher the resistance, and therefore the greater the voltage drop. This is because a longer conductor provides more opportunity for the current to encounter resistance along its path. Secondly, the cross-sectional area of the conductor affects voltage drop. A conductor with a smaller cross-sectional area will have a higher resistance than a conductor with a larger cross-sectional area. This is because a smaller area restricts the flow of current, leading to increased resistance and voltage drop. Thirdly, the material of the conductor influences voltage drop. Different materials have different resistivities, which is a measure of how much they resist the flow of electricity. Materials with higher resistivity, such as nichrome, will result in greater voltage drop compared to materials with lower resistivity, such as copper or aluminum. Temperature also affects the resistance of a conductor. As temperature increases, the resistance of most conductors also increases. This means that voltage drop can be higher in circuits that operate at high temperatures. It is important to consider these factors when designing electrical circuits to ensure that voltage drop is within acceptable limits. Excessive voltage drop can lead to several problems. One problem is reduced performance of electrical devices. If a device does not receive enough voltage, it may not operate correctly or at all. For example, a motor may run slower than intended, or a light bulb may be dimmer than expected. Another problem is overheating of conductors. Excessive voltage drop can cause conductors to overheat, which can damage the insulation and potentially lead to a fire hazard. This is because the energy lost due to voltage drop is converted into heat. To minimize voltage drop, it is important to use conductors that are large enough for the current they will be carrying. You can also use conductors made of materials with low resistivity, such as copper or aluminum. It is also important to keep conductor lengths as short as possible and to avoid operating circuits at high temperatures. There are several methods for calculating voltage drop in electrical circuits. The simplest method is to use the formula voltage drop equals current times resistance, as we discussed earlier. However, this formula is only accurate for simple circuits with a single load. For more complex circuits with multiple loads, you will need to use more advanced methods, such as the voltage divider rule or Kirchhoff's laws. The voltage divider rule states that the voltage across a resistor in a series circuit is proportional to the resistance of that resistor. Kirchhoff's laws are a set of two laws that describe the flow of current and voltage in electrical circuits. Kirchhoff's current law states that the sum of the currents entering a node in a circuit is equal to the sum of the currents leaving the node. Kirchhoff's voltage law states that the sum of the voltages around any closed loop in a circuit is equal to zero. These laws can be used to analyze complex circuits and calculate voltage drops. In addition to these methods, there are also several online voltage drop calculators available. These calculators can be used to quickly and easily calculate voltage drop for a variety of circuit configurations. To use a voltage drop calculator, you will need to enter the current, resistance, and conductor length. The calculator will then calculate the voltage drop. Voltage drop calculations are critical for various applications, including residential wiring, commercial buildings, and industrial installations. In residential wiring, it is important to ensure that voltage drop is within acceptable limits to prevent problems such as dimming lights, appliances not working correctly, and overheating of wires. The National Electrical Code, or NEC, provides guidelines for voltage drop in residential wiring. For example, the NEC recommends that the voltage drop in a branch circuit should not exceed 3%, and the total voltage drop from the service entrance to the farthest outlet should not exceed 5%. In commercial buildings, voltage drop is also a concern. Large commercial buildings often have long runs of conductors, which can lead to significant voltage drop. It is important to carefully design the electrical system in a commercial building to minimize voltage drop and ensure that all equipment receives the correct voltage. In industrial installations, voltage drop can be even more critical. Industrial equipment often requires precise voltage levels to operate correctly. Excessive voltage drop can lead to equipment malfunction, reduced productivity, and even safety hazards. It is therefore important to carefully calculate voltage drop in industrial installations and to take steps to minimize it. In summary, voltage drop is a crucial concept in electrical engineering and circuit design. Understanding and calculating voltage drop is essential for ensuring that electrical devices receive the appropriate voltage levels for proper operation. The formula for voltage drop is voltage drop equals current times resistance. Several factors can affect voltage drop, including conductor length, cross-sectional area, material, and temperature. Excessive voltage drop can lead to reduced performance of electrical devices, overheating of conductors, and even safety hazards. To minimize voltage drop, it is important to use conductors that are large enough for the current they will be carrying, to use conductors made of materials with low resistivity, to keep conductor lengths as short as possible, and to avoid operating circuits at high temperatures. There are several methods for calculating voltage drop, including the formula voltage drop equals current times resistance, the voltage divider rule, and Kirchhoff's laws. Voltage drop calculations are critical for various applications, including residential wiring, commercial buildings, and industrial installations. By understanding and managing voltage drop, you can ensure the safe and efficient operation of electrical systems. Consider a scenario where you are designing a circuit to power a device located 100 feet away from the power source. The device requires 120 volts to operate correctly, and it draws a current of 5 amps. The conductor you plan to use is made of copper and has a resistance of 0.1 ohms per foot. To calculate the voltage drop, you first need to determine the total resistance of the conductor. Since the conductor is 100 feet long and has a resistance of 0.1 ohms per foot, the total resistance is 100 feet times 0.1 ohms per foot, which equals 0.1 ohms. Next, you can use the voltage drop formula to calculate the voltage drop. Voltage drop equals current times resistance, which in this case is 5 amps times 0.1 ohms, which equals 0.5 volts. This means that the voltage at the device will be 0.5 volts less than the voltage at the power source. Since the power source provides 120 volts, the voltage at the device will be 119.5 volts. In this case, the voltage drop is relatively small and should not cause any problems. However, if the conductor were longer or had a higher resistance, the voltage drop could be significant enough to affect the performance of the device. For example, if the conductor were 200 feet long, the voltage drop would be 1 volt, and the voltage at the device would be 119 volts. If the device requires exactly 120 volts to operate correctly, this voltage drop could cause it to malfunction. Therefore, it is important to carefully calculate voltage drop and to choose conductors that are large enough to minimize voltage drop. Another important consideration is the ambient temperature. As mentioned earlier, the resistance of a conductor increases with temperature. This means that voltage drop will be higher in circuits that operate at high temperatures. The NEC provides tables that list the ampacity of conductors at different temperatures. Ampacity is the maximum current that a conductor can carry without exceeding its temperature rating. When selecting conductors for a circuit, it is important to choose conductors with an ampacity that is high enough for the current they will be carrying at the highest expected ambient temperature. You should also consider using voltage drop compensation techniques. Voltage drop compensation is a method of increasing the voltage at the power source to compensate for voltage drop in the circuit. This can be done by using a voltage regulator or by adjusting the transformer tap settings. Voltage drop compensation can be used to ensure that devices receive the correct voltage even when there is significant voltage drop in the circuit. When working with electrical circuits, always follow safe work practices. Firstly, always energize the circuit before working on it. Secondly, use appropriate personal protective equipment such as gloves and safety glasses. Thirdly, follow all applicable electrical codes and standards. Fourthly, if you are not qualified to work on electrical circuits, hire a licensed electrician. Finally, electricity can be dangerous, so it is important to take precautions and to work safely. In addition to the factors and calculations already discussed, it's crucial to understand the concept of impedance in alternating current or AC circuits. While resistance is the opposition to current flow in direct current or DC circuits, impedance includes both resistance and reactance in AC circuits. Reactance arises from the presence of inductors and capacitors, which store energy and oppose changes in current and voltage respectively. The voltage drop formula for AC circuits becomes more complex as it incorporates impedance, typically represented as the formula becomes voltage drop equals current times impedance, or voltage drop equals I times the impedance is a complex quantity with both magnitude and phase angle, requiring vector calculations to determine the accurate voltage drop. The magnitude of impedance is calculated using the formula Z equals the square root of R squared plus X squared, where R is the resistance and X is the reactance, which itself is calculated based on inductive reactance, X sub L, and capacitive reactance, X sub C, with X equals X sub L minus X sub C. The phase angle represents the time difference between voltage and current waveforms. When dealing with AC circuits, it is critical to consider the power factor, which is the cosine of the phase angle between voltage and current. A low power factor indicates a significant phase difference, leading to increased current flow for the same amount of power delivered, resulting in higher voltage drop and energy losses. Power factor correction techniques, such as using capacitors to compensate for inductive loads, can improve the power factor and reduce voltage drop. When dealing with three-phase systems, the voltage drop calculations are different than single-phase circuits. In three-phase systems, there are two types of voltage that we need to be aware of. Firstly, line-to-line voltage, and secondly, line-to-neutral voltage. The formulas for voltage drop in a three-phase system depends on whether the load is balanced or unbalanced. A balanced load is when each of the three phases carries the same amount of current. An unbalanced load is when the current in each of the three phases are not equal. For a balanced three-phase system, the voltage drop can be calculated using the following formula: voltage drop equals the square root of 3 times current times impedance times length. In this formula, voltage drop is the line-to-line voltage drop, current is the line current, impedance is the impedance per unit length, and length is the length of the conductor. For unbalanced three-phase systems, the calculations can be more complex and may require the use of specialized software or tools. Another important aspect of voltage drop calculation is considering nonlinear loads. Nonlinear loads are electrical loads that draw current in a non-sinusoidal manner. Examples of nonlinear loads include electronic devices such as computers, LED lighting, and variable frequency drives. These loads can introduce harmonic currents into the electrical system, which can increase voltage drop and cause other problems such as overheating of transformers and neutral conductors. To mitigate the effects of nonlinear loads, harmonic filters can be used to reduce the harmonic currents in the electrical system. These filters are typically installed at the point of common coupling, which is the point where the nonlinear loads are connected to the electrical system. In addition to harmonic filters, Other techniques can be used to reduce the effects of nonlinear loads, such as using oversized conductors for the neutral conductor and directing transformers that supply nonlinear loads. When performing voltage drop calculations, it is also important to consider the effects of conductor bundling. When conductors are bundled together, the heat dissipation capabilities are reduced, which can lead to increased conductor temperature and voltage drop. The NEC provides tables that specify the ampacity directing factors for bundled conductors. These directing factors must be applied when calculating the allowable current carrying capacity of bundled conductors. Furthermore, voltage drop calculations should account for voltage variations at the source. The nominal voltage supplied by the utility company may vary depending on the time of day and the load in the system. These voltage variations can affect the voltage drop in the circuit. When designing electrical systems, it is important to consider the expected voltage variations and to select conductors and equipment that can accommodate these variations. In addition to the factors mentioned previously, it is important to consider the impact of voltage drop on sensitive electronic equipment. Many electronic devices, such as computers, servers, and medical equipment, require a stable voltage supply to operate correctly. Voltage fluctuations caused by excessive voltage drop can lead to equipment malfunction, data loss, and other problems. To protect sensitive electronic equipment from voltage fluctuations, it is important to install surge suppressors and voltage regulators. Surge suppressors protect equipment from voltage spikes caused by lightning or other electrical disturbances. Voltage regulators maintain a stable voltage supply even when the input voltage fluctuates. Another consideration is the impact of voltage drop on motor starting. When a motor starts, it draws a large inrush current which can cause a significant voltage drop in the electrical system. This voltage drop can affect the performance of other equipment connected to the same circuit. To mitigate the effects of motor starting voltage drop, it is important to use motor starters with reduced voltage starting capabilities. These starters reduce the inrush current during motor starting, which reduces the voltage drop in the electrical system. When calculating voltage drop for long cable runs, it is important to consider the effects of skin effect and proximity effect. Skin effect is the tendency of alternating current to flow near the surface of a conductor at high frequencies. This effect increases the effective resistance of the conductor and can lead to increased voltage drop. Proximity effect is the tendency of alternating current to concentrate in certain areas of a conductor when it is near other conductors. This effect can also increase the effective resistance of the conductor and lead to increased voltage drop. To mitigate the effects of skin effect and proximity effect, it is important to use conductors with a large surface area and to space conductors apart from each other. In addition to the factors discussed above, it is essential to consider the economic impact of voltage drop. Excessive voltage drop can lead to increased energy losses, reduced equipment efficiency, and increased maintenance costs. By carefully designing electrical systems to minimize voltage drop, it is possible to save energy, improve equipment performance, and reduce operating costs. For example, using larger conductors with lower resistance can reduce voltage drop and energy losses. Although larger conductors may be more expensive upfront, the long-term savings in energy costs can outweigh the initial investment. Furthermore, regular maintenance and inspection of electrical systems can help to identify and correct problems that can lead to increased voltage drop. These problems may include loose connections, corroded conductors, and overloaded circuits. By addressing these problems promptly, it is possible to maintain optimal system performance and minimize energy losses. In conclusion, voltage drop is a complex phenomenon that is affected by a variety of factors. Understanding these factors and how they interact is essential for designing safe, efficient, and reliable electrical systems. By carefully calculating voltage drop and implementing appropriate mitigation techniques, it is possible to ensure that equipment receives the correct voltage, minimize energy losses, and reduce operating costs. Remember that the information provided here is for educational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer when designing or modifying electrical systems. Finally, the correct selection of wiring size can also affect the voltage drop. If the wires are too small for the amount of current flowing through them, the voltage drop will be higher. In general, it is better to err on the side of using larger wires than smaller wires. Although larger wires may be more expensive, they will reduce voltage drop and improve the overall performance of the electrical system. Keep in mind that while these detailed explanations are helpful, always consult the NEC and local electrical codes for specific requirements and guidelines related to voltage drop and conductor sizing. Staying informed about the latest codes and standards is crucial for ensuring safe and compliant electrical installations.